In any case, we are talking about entire functions, right? So functions that are holomorphic on the entire plane. And our goal is to get to this thing called Weierstrass factorization. Okay, so Weierstrass factorization basically gives you a way of creating an entire function. So it's basically, so here's like, it starts with a simple question, right? If you have a finite number of points in the plane, and somebody asks you to make a polynomial, to make a function that has zeros at those points, right? Then zeros with certain multiplicities at those points, well, you can do it, right? You just take, z minus that point to whatever power times z minus that second point to whatever power, and so on and so forth, right? You just make a polynomial that does it. Okay, but in the case of entire functions, you might have an infinite number of points, right? So the question will be, if you have an infinite sequence of points that has no limit point, that, so an infinite sequence of points that diverges to infinity, can you create an entire function that has zeros at those points with specified multiplicities? Okay. Right, and so you can't just take an infinite product of linear factors. That doesn't make any sense. So we're going to work our way up to doing that. I think we might even be able to get through it all today. So yeah, thanks to Stein's emphasis on efficiency. Okay, so we're going to start off with this so-called infinite products. Okay, so definition, you have a bunch of points in the complex plane, and you want to talk about what it means to take the infinite product of those points, right, from n equals 1 to infinity. Right. What's the infinite product? So I don't know if you've seen this before. This big pi stands for product, just like the big S stands for sum, right? So this is the infinite product. So the way that Stein does it, he says, well, if he does it in the way that you would probably naturally do it, coming out of a calculus 2 class or something. You'd say, well, look, let's look at the partial products, right, from n equals 1 to k, and then let k go to infinity, right? Says, well, look, if the limit of the partial products exists, then we write it as this thing, right? As the infinite product. Okay, so we say that that this infinite product converges to that value. Okay. Okay. Now I should say that in other books they don't define it this way. They define it in a somewhat different way. So just a comment. In other texts, one has a more restricted definition. Okay, so I'm just going to give this to you because I think you should be aware of it. Like if you read some other book, be sure that you know what kind of definition they're using. So they say the definition goes like this. So if when only finitely many of the Zn are 0. Okay. And 2, for any n naught large enough that a sub n is non-zero for all n greater than n naught, the limit of the partial products from n naught onwards, or after n naught, as the upper index goes to infinity, exists and is non-zero. Okay. If those two conditions are satisfied, then we say that we define the infinite product to be the product of the finite guys from 1 to n naught, and then that limit of everything times everything afterwards. That existing limit that thing that we just said existed. Okay, and it's an easy exercise to see that this is well defined. That it doesn't depend on the n naught, right? You can take whatever n naught you choose, you're going to get the same number. Okay, so one is this is sort of like the straightforward definition, the simple definition, and then this is the sort of more sophisticated definition that people use because you can get sort of nice results. When you develop the theory of infinite products, it's easier to get nice results with this thing. Okay, so you see what it is, right? There's only a finite number of zero terms, and then when you cut out those zero terms and take the products of everything else, that converges to a non-zero number. Okay, that converges to a non-zero number, and then you take the product of those two things, right? The finite guys, which may well be zero. If one of them is zero, then of course that's zero, and then this non-zero tail thing. Yeah, Jane.
I was just going to ask if that the infinite product being zero causes any problems.
No. Yeah. So no. If this is zero, then it's zero. Yeah. Yeah. Yes, Noah.
Is the Zn and the I there supposed to be An?
Oh, I'm sorry. Yes, this should be an A. Yeah. Sorry, I probably wrote it two different ways in my notes, but yeah, I think it's okay now. Yeah. So just to give you an example. Okay, so here's some kind of funny examples. If I take something like this, the product of n as n goes from 0 to infinity. Okay, so that's 0 times 1 times 2 times 3 times 4, etc., etc. Okay, then that converges in the simple sense, right? Because the partial products are all going to be 0, right? 0 times 1, 0, 0 times 1 times 2, 0 times 1 times 2, 3, 0, right? All the partial products are 0, and so in Stein's sense, that's just going to be 0, okay? But in the restrictive sense, this is considered a divergent product, right? Because, right? So you remember what you do? You chop off the zeros, right? And then you look at the partial products of the rest of the guys, and that should converge. That needs to converge to something non-zero. Well, this doesn't converge, right? As you take, this is n factorial. As n goes to infinity, it goes to infinity, right? So this in sense 2, this doesn't. So in sense 1, converges. In sense 2, diverges. Right, because of this, because of the second part. Right. Yeah, Joseph.
Are there different names for these different types of convergence?
They're both called just convergence of an infinite product.
Great.
Yeah, whatever author, they just call it. We say a product, an infinite product converges if blah. So I was looking through different books, and So like Stein, of course, uses a simple one. So does Conway, John B. Conway, in his books. And then Greene-Krantz actually used this one, as does Knopp, which is what I used when I was an undergraduate. What our professor used when I was an undergraduate. Yeah. Yeah. So, like I said, I think it's just a matter of efficiency, right? Like with this definition, you can create an entire structure you can create sort of a structure of a more sort of a useful theory of infinite products. And then this one is sort of like, we're going to get enough to get Weierstrass factorization. That's all we want.
Okay, thanks.
Another example. Okay, so does this converge or does this diverge with respect to the two definitions? 1/2 to the j as j goes from 1 to infinity. I'll let you just maybe like talk to a neighbor.
Yeah.
Do you think it's convergent? This is I'm not 100% sure.
Yeah, I think in the Stein.
Oh, is that a Z?
Oh, it's like the
I think
limit.
it's
J. Oh, to the J.
One over 2 to the J. Yes.
Partial zeros. And then the
None of them are zero.
Oh.
It's 1 over 2 to the Q.
My definition you cut out.
Yeah, the limit exists.
Same definition you cut out.
Wait, is
Yeah.
partial
And then.
Oh,
That's
yeah, it's.
Yeah, I have.
So
I think so, yeah.
for it to converge, the limit
Check the
exists in the
The limit of the remainders of it is 0.
Yeah.
Wait, if I'm understanding this right. No, sorry.
Oh, right,
Limit
yeah,
of
it's
the,
non-zero.
I don't, but he's not.
This is, you're like opposite definitions.
I think the
I think my converge is zero, right?
Yeah, no. Limit of the remainder, you mean remainder product, right?
remainder product, yeah.
Okay,
There's-
what do people think? With respect to 1, does it converge or diverge?
Convergence.
Converges, right? Because it's just, 1/2 multiplied by itself, right? So it converges. What about with respect to 2? Converge or diverge?
It doesn't converge
Why not?
because the limit is 0.
Because the limit is 0, right? Because, right, so you take, yeah, because of this condition. It has to be that the tail, the product, the tail has to converge to 0, to non-zero, something non-zero, right? So yeah, so this diverges with respect to the product. Converges and diverges, right? You would chop it off at some certain point, whatever point you like, right? And then look at the limit of the partial products as, and the limit of the partial products is going to be 0, but this has to be non-zero. Okay, yeah. Yeah, so one remark, sort of obvious, that if it converges with respect to 2, then what am I going to say? You can probably just guess, yes, no.
Like then it also converges with.
It also
respect to one.
converges with respect to 1, right? Because if it converges with respect to 2, that means that you have something like this, right? Which means that the limit of, then, clearly the limit of the partial products of the whole thing is going to converge. Yeah. So converges with respect to 1. Right. So this is like if you wanted to call it something, this is like the stronger condition. Right? This is stronger, more constrained version. Okay. Okay. Another observation. with respect to Stein's definition, if none of the factors are zero, and the product is not zero, then you know that the limit of the partial products is this number, right? The limit of the partial products is this number, and that tells you that if you look at say zk to the n plus 1 over zk to the n plus 1, take the product to the n plus 1th term divided by the product to the nth term. Well, that's just going to be the n plus 1th term, right? Right. That's the n plus 1th term, right? And as n goes to infinity, the top and bottom are going to go to the same thing, right? And so that tells you that the limit of the zn's is 1 as n goes to infinity, right? Because the products go to the same thing, right? And that's in definition 2 we don't that happens automatically, right? In definition 2, there's only a finite number of zero terms, right? And then afterwards, the partial products converge, right? The partial products of the tail converge, and so that also tells you that these guys would go to 1. Okay, so what's the point? The point is that it's illustrative, or maybe it's sort of like it's maybe suggestive. I'm not sure what's the right adjective. It's suggestive to think of this product as rather a product of things of this form, 1 plus something, right? So like you know that roughly speaking, the zk's are going to tend towards 1. So what's important is this little difference from 1, right? It's important to think about this thing rather than about 1 plus that thing. Okay, and that is how we're going to state our first theorem. Okay. So here's a theorem about convergence. Okay. So here it is that if the sum of the absolute values of the A sub n converges, then the infinite product, 1 plus A sub n, converges. Okay, and this is the theorem that we're going to use when we go for this is the theorem that's going to be useful when we go for the Weierstrass factorization. Okay, so notice that the converse is false. Right? If the product converges, that does not mean that that the sum of the absolute values of the deviations converges. You know, we can look at the example we had before, right? You know, 1 plus negative a half, that converges in the sense of Stein, but you know, the sums of 1/2 of course diverges. Right? This thing converges, but summation this diverges.
Why is
Yes.
the product over 1/2 converge?
This is just going to be 1/2. I'm sorry. Yeah, this is just 1/2 times itself infinitely many times.
Oh, I see. So
The thing that we
converges
have-
to 0, but
converges
and
to
it's
0.
okay that okay.
In the Stein sense, remember?
Right.
So Stein, yeah, in the sense of Stein, the simple sense, which is what we're going to be using.
So is the converse true in if you assume the stronger sense? Or?
No, wait. No, it's not true in that sense either. Yes.
The only reason I'm confused is I thought we just showed that if a product converges, then like the terms of the product have to go to 1. What was that? The other sense of convergence?
If the product converges, but remember we also had to assume that the product went to something non-zero. That
Okay.
was part of it.
Okay,
And this
I
product
understand.
goes to 0.
I understand.
Yeah.
Thank you.
Okay, so here's the proof. You say, well, this thing converges. So eventually, past some point, all of these guys are smaller than 1/2, right? Because of convergence. Right. So okay, so we can, without loss of generality, just assume that all of them are smaller than 1/2. Right. If some of them are bigger than 1/2, we can just there's going to be a finite number of those guys anyway. So we just there's going to, in that case, there would be some finite part, and then we would be dealing with these guys who are all smaller than 1/2 anyway. So let's just assume that they're all smaller than 1/2. Okay. So now we write 1 plus a sub n as e to the log 1 plus a n, where this is the principal branch of the log. Okay, that's okay, right? Because they're 1 plus something that's smaller than 1/2, right? So all of these terms lie here. We don't have to worry about terms that go around or something like that, right? They're all inside here. This makes sense. This makes sense as long as a sub n is smaller than 1 in size. Right. Okay. So in that case, so we can write right. We want to show that the limit of these partial sums, partial products, that these guys converge, that this limit converges, right? So we're going to use this to rewrite it. Take the partial product, and we write it as the product of E log 1 plus a sub n, right? But that turns this into a sum, right? This becomes the sum of the logs, e to the sum of the logs. Right? Okay. And so now we're hoping to see that this thing converges. Okay. Does this converge? So what we're going to do is so claim for z smaller than a half in modulus, the absolute value of the log is controlled by 2 times the absolute value of a sub n. So what we get from that is that that this sum here the size of this thing is controlled by the sum of the absolute values of the logs, which is controlled by the sum of these guys. But that's finite, right? That's finite by assumption. That's finite by assumption, and so we get that this thing is going to converge. So let me prove that bound. The bound is pretty straightforward. So y is if absolute value z is smaller than a half, then the size of the log of 1 plus c is smaller than 2 absolute values. Okay, so this is just using the power series. So we use the power series expansion that we mentioned way back when we were talking about the principal log. That log of 1 plus z is the same thing as negative summation -1 to the n, z to the n over n, as n goes from 1 to infinity. And this is valid in the unit circle. Okay, and then we say, well, look, if we take the absolute value of that, that's smaller than, less than or equal to the sum of the absolute values, right? So we get z to the n over n from 1 to infinity. Right? I'm going to factor out one of the z's. Okay. So we get the absolute value of z times this term, right? But z was assumed to be less than 1/2 in modulus, right? So we just get summation 1/2 to the n minus 1 over n as n goes from 1 to infinity. Right? Well, that's smaller than that's smaller than summation 1/2 to the n minus 1 as n goes from 1 to infinity, which is 2. Yeah.
Can we not do this by expanding out that product and saying, well, you get something that looks like the sum of all an, but also something that looks like some aj times the sum of all an minus 1, and then some aj ak times the sum of all a1 through an minus 2. And so all of these are controlled by absolute convergence of the sum.
Can you say that one more time?
Can you not just expand out that product and then it follows by, well, the way you have to expand it, and the fact that all of the an are less than 1, that so all of these sums are going to be strictly less than, or at least less than or equal to the partial sums of the series that we already know converges.
So you're saying just expand it out? Like this is going to be 1 plus a1, 1 plus a2, 1 plus an?
Yeah.
And then,
So if you expand it out, you get something that looks like the partial sum up through an, but then also you get something that looks like a1 times the partial sum 2 through an, and so on and so forth. And then you can pick 2, you can be like a1 and a2 times, but all of the a's have absolute value less than 1 after some point, and
so they're going to vanish eventually.
so all of these sums are controlled by absolute convergence of the big sum.
Wouldn't the number of those sums be approaching infinity though, without approaching infinity?
Oh, yeah.
Yeah, I'm not sure, but I'm not sure. Yeah. Yeah, I think no. Were you the one who said would there be infinitely many of those sums?
Yeah.
Yeah, I think that's a reason. That's a problem. Yeah. Okay. Okay. In any case, is everybody okay up to this point? Right. So we assume that the a sub n's are all small, right? That allows us to bring in the log. That allows us to change this thing into a statement about a sum, right? Right. And then using this bound here, we see that sum converges because that sum is bounded by this, and we assume that this sums converge. Right. So what does that give you? Right. That gives you that this thing is gonna converge to something, right? Which means that that our partial products do converge.
Just back on the expanding the thing, like the infinitely many sums would have infinitely many terms less than a half, say, in front of them, right? So those would all go to 0.
Let's talk about it after. Let's talk. I don't think I can just yeah. Let's talk about it after. Possibly, I don't know. Let's talk about it after. Everybody okay? Any questions? Okay. So in any case, so this so this is going to converge to some number, right? E to the, I think e to the b. That's what. Anyway, it converges. Because of the claim. Okay, so that gives us this useful thing that says, as long as we know that the sums of the that the deviations, the sum of the deviations converges absolutely, then the partial product of then the infinite product of of these terms, 1 plus the deviations exists. There's a remark. Notice that under this condition, that is that the sum of the deviations is finite, if all the 1 plus a sub n are non-zero, then the product is going to be non-zero. Okay, because it's e to the something. Okay, it's e to the something. Okay, so in other words, if you get 0, it must be because if you get 0, then one of the terms must be 0. Okay. Okay, I'm just going to erase this. Okay, so from there, we're going to go to products of functions. Okay, so our real goal is to get to products of holomorphic functions. Right? Because we want to get, we want to do the Weierstrass factorization, which is going to involve an infinite product of functions. Okay. So we need to, we need the following tool. So you have omega and open set, and you have an infinite number of holomorphic functions. Okay. You have an infinite number of holomorphic functions such that their distance, each of them has a controlled distance. Sorry, let me write this as capital F, because that's how I have it in my notes. Such that their distance from 1 is controlled by some bound. Okay, for all z in omega. Okay. Then the theorem says that if the sum of the m sub n is finite, then in fact the infinite product converges uniformly to some f. To some f, which is going to be holomorphic. Okay, so this is sort of like the Weierstrass, sort of like Weierstrass M-test. Right. Right. Weierstrass M-test. Right. As long as your functions are bounded by things that whose sums converge, then your functions converge uniformly. The sum of your functions converges uniformly. Right? This is sort of like the product analog of that. Right? As long as your distance from 0 is controlled by some bounds whose sum is finite, then your product converges uniformly to some function. Okay. That's probably how you want to think about this. Okay, everybody all right? How much did you not sleep last night? Did everybody sleep okay last night? No. In my previous class, students who didn't go to sleep until like 5 or 6 or something like that.
It was called at like 5.
Oh, is that right? So I guess that's why. Yeah, I went to sleep at 10. It was pretty obvious by that point. Okay. Okay, so here's the proof. You say, well, look, we just showed that, you know, if we let a sub n z be fn z minus 1, right? So that these guys are bounded by the bounds that we have, that we're given. Then, as long as the sums of the absolute values are smaller than infinity, then this thing converges. Right? That's exactly what we just had, right? We just said, as long as you know, if you have some number a sub n, and you have some bounds on those numbers, and the sums of those bounds are finite, then, you know, the sum of the f sub n is 1 plus a sub n, right? And this is your 1 plus a sub n. And these guys converge, right? So that's the theorem that we just showed. So we know that each of these things converges, right? We know that each of these things converges. The only thing we need to show is that it converges uniformly, right? So it suffices to show that convergence is uniform. Right? But when we did the convergence, that convergence is only going to depend on that convergence depends on these numbers. These numbers are independent of z, right? And so, you know, that implies that the convergence is independent of z, so the convergence is uniform. Okay, so that's basically the reasoning right there. Let me lay it out a little bit more clearly. Right? So, the point is that the m sub n are independent of the z, so the convergence is uniform. Just to lay it out a bit more explicitly, you say, well, look, you know, if we're looking at this 1 plus a sub n to the n, just going through the same argument as we did before, right? That's going to be e to the summation log 1 plus a sub n z, right? You know, and again, you know, that converges since summation of the absolute values is controlled by twice the summation of these guys, right? 1 plus a sub n z. Right. This was the same argument that we went through last time, right? That this thing is going to be controlled by twice. This partial sum is going to be controlled by this partial sum, right? But this partial sum is controlled by this, right? And that's finite. Right. So what the point is that we can make the point is that we can make summation from n to m we can find an n naught such that if n and m are greater than n naught, then this thing is smaller than whatever epsilon we choose. Right? So given any epsilon, does that make sense? Like this thing is controlled by this, which is finite, right? And so we know that we can make this tail as small as we desire, right? Since this thing converges, we can make this tail as small as we desire, right? But making that tail as small as we desire guarantees the uniform convergence, right? Because I know, is this clear enough, or do you want me try to lay it out a bit more clearly? Right? You're trying to show that that this thing converges uniformly. Right? That is to say that this thing converges uniformly, right? Well, if you take a difference of, if you take a difference of those terms, right? Like e to the summation to the m minus e to the summation to the n, and say that n is smaller than m. Right? Then if you factor out this guy, right? Then you're going to get e to the summation n plus 1 to m minus 1. Right? Now, this term is bounded. This term is bounded, right? And then this term, we can make this thing as close to 0 as we want. Right? We can make this thing as close to 0 as we want, and so we can make this thing as small as we want, and that gives us the uniform bound.
So it's bounded uniformly because the Mn bound is...
Exactly, yeah, because of the Mn bound. Yeah, in the book, Stein just says, look, Mn doesn't depend on Z, so it's uniformly bounded. So I'm just trying to lay it out a bit more clearly. And good old Stein, always clear. Yeah. Okay. Yeah, if you go on in the series, you'll find that it becomes more and more opaque as time goes on. So by the fourth book, he just says, like, it's clear that this whole thing is clear. Yeah. Okay. So what's the point? The point is that as long as we have this control over this sort of control over the distance to 1, right? As long as we have this control over the distance to 1, then we have uniform convergence of the products of the infinite product to a holomorphic function. So we get that infinite product of holomorphic functions is still a holomorphic function as long as we have this Weierstrass kind of condition. Okay, that's the point of this. Okay, we're not going to finish today. Okay, so now we want to go for Weierstrass factorization. we may get through the first lemma.
Why is the product holomorphic?
Why is the product holomorphic? Because you have a uniform convergence of holomorphic functions.
Oh, okay.
Right, we had some result from some time ago. Okay, so let me state the theorem. It goes like this: let A sub n be any sequence in C such that A sub n goes to infinity. Then there exists an entire function with zeros at the A sub n. Some of those A sub n are allowed to be the same, so you can have you can make the multiplicity in that way. With zeros at the A sub n and nowhere else, and nowhere else. Okay, so the way we're going to do it, we're going to construct it as an infinite product of these things called elementary factors. So here's what we're going to do. We say notate E naught of Z is just going to be 1 minus Z. So that is it has a 0 at 1. Okay. And then for EP of Z, we make that 1 minus Z times E to the Z plus Z squared over 2 plus ZP over P. Okay, so these guys, the E sub P, are called the Weierstrass elementary factors, excuse me. Okay, and these are going to be the things that we multiply, that we use to construct the function. So ultimately, the function that we construct will look like Z to the M. So you throw in something for 0 if there's something at 0, times the infinite product E sub n Z over A sub n. N goes from 1 to infinity. Okay, because you see that, notice that these E sub P are all entire. They're all entire functions. And what's that? At 1, they take a value 0. So they all have zeros. They all have zeros at 1. Of order 1. Okay. More importantly, also importantly, this term in the exponent comes from the power series expansion of log 1 minus Z. So this is Z minus 1, Z smaller than 1. Okay, so what's the point here? As P gets larger, then this thing starts looking more like E to the negative log 1 minus Z, right? In other words, 1 over 1 minus Z, right? so the factor starts looking more and more like 1. So you've got something that has the 0 at the right place and gets closer and closer to 1 as time goes on. So you've got a better chance of this thing actually converging when you take the infinite product. Right. You want your terms to be close to 1 for the infinite product to make any sense. So this is Weierstrass's clever idea. Right. Okay. So yeah, I think we are not going to. Yeah, let me just. So the main lemma is the following: that for z smaller than 1, the distance of the factor from 1 is controlled by z to the p plus 1. Okay. So we have a concrete bound on the distance to 1, right? In terms of the size of z. Okay. So yeah, I'm afraid I don't think I'll be able to get through that in the next couple minutes. So we'll do it all. We'll do the lemma and then proof of Weierstrass factorization next time. Okay, that's it.